This is a collection of problems that we would have normally done in a lab period when the exam that covers Chapter 6 is approaching, all having to do with using energy methods because there's just a lot of different situations that it can be applied in, and a lot of them feel very different until you've done a whole lot of problems. So let's go through them one by one. These are my solutions that I'm sort of flipping through here. Problem 1. Use energy methods. A half-kilogram ball is thrown straight up at 3 meters per second from Earth's surface. Find its speed after it's moved a quarter of a meter upward. Ignore air resistance. So in this case, I really have two choices. I could either take my system to be just the ball, and then I could use the work kinetic energy theorem, but why not use our other relationship that involves potential energy by taking our system to be the ball plus the Earth and that internal gravitational force between them? We'll treat it as an internal force and we'll associate a potential energy with it. That means that there are no other forces, given that we're ignoring air resistance, no other forces are doing work on the ball as it rises from the initial state to the final state. And so sometimes I say that's the system is everything, because any forces that are acting on the moving parts of the system are already thrown in the system. That means the net work done by all external forces is 0, and that's equal to 1/2 mv final squared minus 1/2 mv initial squared. The initial speed is 3, v final is what we're after, plus the change in potential energy, and we use the gravitational potential energy near the surface of the Earth, mg times y final minus y initial. It's going up, so y final minus y initial is positive 0.25 meters. The m's all cancel out, so we didn't really need the 1/2 kilogram that was given there. And we can solve for v final. Problem 2, again, use energy methods. I'm saying that here because in a lot of these cases we could actually use kinematics, but I want you to practice with using energy methods. Half-kilogram ball thrown upward from the Earth's surface, same initial speed, find the maximum height. So in this case I'm going to take release to be initial, maximum height to be final. That means v final is 0, v initial is 3, and mg times y final minus y initial, or delta y. That delta y is what we're after, how high it goes above the release point. So the m's cancel again, and we're going to solve for delta y in this case. Just a little bit under 1/2 meter. Use energy methods. A box on a frictionless inclined plane is given an initial push downward. So we give it a shove in the direction down the plane. There's no friction, and it slides down. Its mass is 2 kilograms. Initial speed is 0.75 meters per second. And we're given the angle of the incline. Find its speed after it has moved 1.5 meters down the plane, ignoring air resistance. So in this case, I said the system is everything. It's probably a little bit less confusing if you say the system is the box plus Earth. Gravity is an internal force, but we'll leave the normal force because it's a little bit confusing as an external force. Thankfully, that normal force doesn't do any work because it's always aimed perpendicular to the direction the box is moving, so it does 0 work. So this is our relationship. Net work done by all external forces, the only external force is the normal force, and it does 0 work, is equal to 1/2 mv final squared. That v final is what we're after, minus 1/2 mv initial squared, and we're given v initial. And in this case, it's going down by a certain distance, and we've got to calculate that. It's not getting closer to the Earth by 1.5 meters. We need to know this vertical distance right here. If you can see my tiny little cursor thing there. This distance. So we got to draw this little right triangle in with a 40-degree angle in it and say, I know the hypotenuse is 1.5 meters, but I want this vertical side over here, and it's going down by that amount. So it's a change, a negative change in y. If you look at the right triangle, the length of this side is 1.5 times sine of 40 degrees. So it's going down by that much. Solve for v final, and you get 4.41 meters per second. A box on a frictionless inclined plane is given a push up the plane. Okay, same initial conditions. Find how far it travels up before momentarily coming to rest. So it's the same problem. Instead of pushing it down, we're pushing it up. How far does it come before it just stops and starts going down again? And so initially, we know its initial speed. Final speed is 0 because it's at that turnaround point. And it's y final minus y initial. we could say initially, if you want, you could take this to be your variable, and that would mean we would be finding this side of the right triangle, the vertical side of the right triangle. Then you'd have to use that to solve for the hypotenuse. Or you could say, hey, look, in terms of the hypotenuse, the vertical side is the hypotenuse delta x times the sine of 40 degrees. So I could just plug that in right away and then say, it's delta x that I'm after. That's how far it moves up the plane direction. Solve for it. Okay, half-kilogram ball attached to a spring anchored to the side of a spacecraft. That's supposed to mean we don't have to worry about gravity. We're in deep space. It's compressed 0.3 meters and released from rest. Find the speed of the ball when it's 0.1 meters from equilibrium. So that means x initial is 0.3 meters, x final is 0.1 meters, and we'll take the springs to be an internal force. So my system is the moving block plus whatever it's attached to, which isn't going to move, the side of the spacecraft. And the spring force is an internal force. There aren't any other forces acting on moving pieces, so the net for work done by external forces is 0. That's equal to the change in the kinetic energy, and it's released from rest, so this part is 0. We're after that V final. And in this case, we know x final is, well, it's compressed by 0.1 meters in the final state. So technically, x final is minus 0.1. It doesn't really matter because we're squaring it, so the minus sign is going to go away. When I put in a negative number for x final, the minus sign goes away. Similarly, the initial x is negative technically, but it doesn't matter. When we square it, the minus sign goes away anyways. The only unknown is v final, so that's going to be the speed when it's that much closer to equilibrium. 6. Use energy methods. Half-kilogram ball attached to a spring. Attached to a spring in outer space. I think it's supposed to say attached to the side of a spaceship with a spring. Same situation as before. It starts in its equilibrium position, but someone gives it a whack with a bat and gives it an initial speed of 4 meters per second in the direction of compressing the spring. So it's essentially instantaneously moving at 4 meters per second while it's in the equilibrium position. That's our initial condition. And the final we're going to use is when the spring is maximally compressed and the ball comes to rest. So in that case, again, we'll take our system to be, take the spring to be an internal force between the spacecraft and the ball. So there are no external forces to do any net work. Here's our delta KE. We know it's coming to rest in the final state when the spring is maximally compressed, so V final is 0. We're given V initial, and then we have the change in spring potential energy, and it's x final that we're after, how much it's compressed from equilibrium. We'll only be able to find out x final to a plus or minus value, but we know that when it's compressed, x final is technically minus 0.283 meters, but we're asked just for a distance, so usually you just give that as a positive number when you answer. X initial is 0 because in the initial state when it's whacked with the bat, it was in its equilibrium position, which by definition for a spring, when we're using this potential energy formula, by definition, when it's in equilibrium, that's x equals 0. So the only thing to solve for there is x final. And when you undo the square, you get a plus or minus, and that means, yeah, it could have been compressed or stretched, but we know from the statement of the problem that it is compressed. In any case, the magnitude of it's the same number. Problem 7. Here a ball is attached to a vertical spring at the surface of Earth. The other end of the spring is attached to the ground. It's compressed 0.3 meters from equilibrium and released from rest. Find the speed of the ball when it is 0.1 meters below equilibrium. In other words, the spring hasn't finished uncompressing, but the ball is still moving upward, presumably. And so in this case, I'm going to take my system to be everything. In other words, I'm going to take the gravitational force and the spring force to be internal forces, and they've got their potential energy functions, 1/2 k. I call it 1/2 k y squared because I'm taking y to be up, and mgy. And so the net work done by external forces is 0 because there aren't any external forces if we're ignoring air resistance. And that's equal to delta Ke plus delta Pe. And I've got two delta Pe terms in this case. Y final is going to be minus 0.1, but it doesn't matter because I'm squaring it, that it's negative. Y initial is minus 0.3. Again, it doesn't matter because I'm squaring it there. It's gone upwards in y by 0.2 meters, so delta y is 0.2 meters. And it's released from rest, so V initial is 0, and V final is what we're after. So we can just unsquare it and get our answer. Problem 8. A 30 kilogram rock is released from rest 1 moon radius above the moon's surface. That means the initial radius, if we're using the minus gm1m2 over r potential energy formula, is going to be 2 times the radius of the moon. What's its speed just before striking the surface? So it's released from rest 1 moon radius above the surface of the moon. I'm going to take initial to be release, final to be just before it strikes the surface. Let's take our system to be essentially everything, the rock plus the moon. Gravity is an internal force. There aren't any external forces to do work, so the net work by external forces is 0. That's equal to delta Ke. We're after V final, and V initial is 0, plus delta Pe, and delta Pe involves this expression. Pe gravitational is minus g times the mass of the rock times the mass of the moon divided by the radius. So we got to do that in the final case, and being very careful about those minus signs, subtract off the initial potential energy with its own minus sign. Put in those parentheses. The initial distance of the rock from the center of the moon is 2 moon radii. The final distance is 1 moon radii. When it strikes the surface, it's 1 moon radius away from the center of the moon. Solving for all of that stuff, you got to put in the radius of the moon and the mass of the moon that are given there. You can solve for V final. It's a big number, but we're dropping something from way above the surface of the moon, so that's not surprising. Same rock is launched directly upward from moon's surface. What's the escape speed for the launch? In other words, what's the smallest launch speed so the rock could have and never fall back? So what that means is, as we discussed in the videos, the final state is when the rock is really far away from the moon, essentially at r equals infinity from the center of the moon, and its final velocity is very close to 0. So we're going to take V final to be 0 and r final to be infinity. And the initial state is when it's launched, and we want to know V initial. So again, same system, no external forces to do work. Delta Ke, V final is 0, so we'll plug that in there. V initial is what we're after. R final, oh, I'm sorry, I'm looking at the wrong problem. That's why I'm confused. Yes, so V final is 0, V initial is what we're after, R final is infinity, and R initial is the radius of the moon. That's when it's launched from 1 moon radius above the center of the moon. Solve for V initial, and we get 2,400 meters per second. Notice it's got to be bigger than the 1697 we got before, because if it fell from rest at 1697 and hit the surface, if it's launched with that same speed at the surface, it would go up to the same height it was released to up here. It's got to go farther than that or it would fall back. So it's got to have a bigger initial speed. 9. A half-kilogram ball is thrown upward at 1,000 meters per second from the moon's surface. Find its speed after it's moved 30,000 meters upward. Same system, no work done by external forces because the only force is internal, and we're going to use this potential energy because it's a conservative force. So find its speed after it's moved 30,000 meters upward. So that's going to be our final, and V final is what we're after. We're given V initial, that's our 1,000 meters per second. The final R is the radius of the moon plus an additional 30,000 meters, and the initial R is the radius of the moon. Plug that all in, and we can figure out what the final speed is, 949 meters per second. Problem 10. Half-kilogram ball is thrown straight up at 1,000 meters per second from the moon's surface. Find the maximum height to which it rises. Same setup. Initial is going to be when it's released. Final is when it's at its maximum height. When it's at its maximum height, the final speed is 0. We're given the initial speed, that's 1,000. Our final is what we're after, right? Or at least it's almost what we're after here. So we're going to solve for that. And our initial is the radius of the moon. So we solve for our final. That's not how it's asked. It's asked, find the height to which it rises. This is the final distance from the center of the moon. If we subtract off the radius of the moon, we'll get the height that it rises above the surface of the moon, which is 357,000 meters, apparently. 11. Half-kilogram ball launched upward with a 30 meter per second initial speed. Suppose it rises to its maximum height and air resistance does minus 50 joules of work. So here we're not ignoring air resistance, but we know how much work it does. Find the maximum height above the launch point the ball reaches using energy methods. So in this case, I'm going to take my system to be the ball plus the Earth. Gravity is an internal force, but I'm going to leave the air resistance external, as we always do. And so the net work done by external forces is minus 50 joules. That's equal to 1/2 mv final squared minus 1/2 mv initial squared, and v final is 0. We're going to take final to be when it reaches that maximum height. It's no longer moving there. And v initial is 30. Plug that in there. Plus mg times y final minus y initial, and we're after that delta y. So we're going to solve for y final there, 35.7 meters. A 2-kilogram block is given a 3 meter per second initial push on a rough horizontal table with a given coefficient of kinetic friction. Find the work done by friction after it has slowed to rest. I think this is actually a problem that we did on a worksheet in class, but in any case, here we can use the work kinetic, we can take that friction force to be an external force, and so we'll take, in fact, we can just take our system to be just the block, and in this case we'll take all forces acting on the block, which is friction, normal force, and weight force, to be external forces. The net work done by external forces is, well, let's see, the normal force does 0 work, the weight force does 0 work because they're perpendicular to the displacement. So the net work done by all external forces is just the work done by friction. That's what we're after, and that's 1/2 mv final squared minus 1/2 mv initial squared, and the change in kinetic energy. And if it's slowed to rest, so if we take the final state to be when it's come to rest, v final is 0. We were given v initial, so we can calculate what the work done by friction is. And of course it's negative. It's always pulling back against the direction it's going. Similar setup, except in this case we want to find the speed of the block after it's moved 1 meter. So in this case, we want to know v final. We don't know that v final is 0 here. It's presumably still going after it's moved 1 meter. So we want to know that v final. We know v initial. This is, again, the net work done by all external forces, but the other two do 0 work, so we only need to calculate the work done by friction. So in this case, we're going to have to calculate this. It goes 1 meter sliding distance, mu kinetic times the normal force, and in this case the normal force balances out the weight force, and it's doing negative work, so I got to put that minus sign in front of it, and that allows me to solve for v final. So it started out at 3 meters per second. Here it's still moving at 1.77 meters per second after it's moved 1 meter along its path. Box on an inclined plane is given an initial push downward and slides down with friction. So in this case, we're given the mass, we're given the initial speed that we push it with, we're given the kinetic coefficient of friction and the angle of incline. Find its speed after it's moved 1.5 meters down the plane. So I'm going to take the system to be the box plus the Earth. We'll leave friction to be external, but take gravity to be internal. So the net work done by all external forces is just the work done by friction. It's a negative amount of work, and I've got to figure out what the friction force is, and I can do that using a little free body diagram over here. And in this case, I've got to figure out that, using the usual methods, I didn't show all the work here, but we can figure out that the normal force is mg times the cosine of 40 degrees. Then the friction force magnitude is mu kinetic times that. So mu kinetic times mg times the cosine of 40 degrees. That's the friction force, and to get the work done by friction, it's a negative work, friction force times the distance it moves. Okay, so that negative amount is the work done by friction as it moves 1.5 meters down the plane. That's equal to the change in kinetic energy plus the change in gravitational potential energy. We're after that V final. V initial was given in this problem. And in this case, we have to do a little bit of work to figure out how much closer it gets to the Earth in going 1.5 meters down the plane. It doesn't get 1.5 meters closer to the Earth. We need to figure out this vertical side here, which is 1.5 times the sine of 40. And delta y is negative. Whenever we use the potential energy, gravitational is mgy. The convention is plus y is up, so it's going down in y as time goes on. So we need that minus sign there. Otherwise, we'll definitely mess things up here. When all that's taken into account, we solve for V final, and we get V final as 3.72 meters per second. I'm not sure what this is referring to in my solution here. Okay, I see. I understand now. This is just the same. Just forget about the thing that I crossed out. This up here is the work shown for the last problem on the worksheet. For some reason, I did it up above. I'm not sure why. A box on an inclined plane is given an initial push up the plane and slides up with friction. Its mass is given, initial speed is given. How far does it go up before it comes to rest? So again, we'll take friction to be an external force, but we'll take gravity to be internal. So the work done by friction will be negative because friction is always going back against the direction it's moving. That's why I put the minus sign in there. We got to figure out what the friction force is in this case, and it's the same magnitude as it was before, same as above. And we want to know how far it goes. So the work done by friction depends on how far it goes, right? It's the force x times delta x, and we don't know that delta x, so that's our unknown here. We're going to solve for delta x. So work done by external forces is equal to delta ke plus delta pe, 1/2 mv final squared. V final is 0 if it's when it comes to rest. V initial, we know that was given in the problem. And then the change in gravitational potential energy, it's going up the plane, so it's increasing in potential energy. Delta x is the distance it moves along the plane, so delta x times the sine of 40 degrees is the vertical distance it moves. That's our delta y. So this is mg times delta y. We can cancel out all the m's there to simplify things. Put everything that doesn't involve a delta x on the left-hand side, everything that does on the right-hand side, factor out a delta x and divide by this junk that's multiplying delta x, and you get delta x is 0.0636 meters, or 6.36 centimeters is the distance it moves up the plane before coming to rest. And that's the end of our long practice worksheet.